Hello there, and welcome to this collection of notebooks and tutorials on machine learning for audio signals. This is a course offered by Professor Shula at the Ilmenau University of Technology. I am Renato, the instructor for these tutorials, and on this notebook we will talk about neural network as function approximator and regression. So let's get started. We can use a neural network to approximate a function. For example, y equals to a function of x. In our simple example, x is a sample, a one-dimensional sample, and y is the target, also a one-dimensional, also called regression. This function could be, for instance, an audio signal, like a tone, which could be a sinusoidal function, for example. Here, x would be the time dimension and y would be a sample from or to the sound card. In pytorch, we have a torch.syn function, which directly produces a torch tensor, and also a torch rand_n function, which produces random numbers according to a Gaussian distribution with zero mean and unit variance. We can use this to simulate a microphone and pick up noise, for example. So we generate our target function like this. So here we are setting the number of samples in our signal. For our input, we're generating n times steps for x. This is what we're doing here. Then we are reshaping to have the last dimensional for the signal and the first dimensional for the batch size n, capital N, that we're defined here. Then we are using this torch.syn, and we are generating two periods of a sinusoid that will be used for training, and we are adding some noise. So here we have x, so it's this array of elements, and this is pi, and then so here we are generating two periods of the sinusoid, and then we're adding some noise using this rand_n function. So often we want our network to interpolate the function between the training samples and also to extrapolate beyond the training samples. Hence, we construct a validation set which has the x samples between the integer values of the training set and extend it to beyond the length of the training set. We can see how robust our network is against the noise in the training set. We also add some noise. So for a validation set, the test to test the generalization with new noise, so this is what we're doing. We're generating now 2 times capital N time steps for x, for extrapolating beyond n, so we have a signal that is 2 times longer than what we are going to train our network with. And also we are reshaping again, and pay attention that now this is shifted by 0.5 compared to the training set for interpolation between the original sample points. And we are reshaping here, and now we have our validation target. Again, we are using torch_syn and adding some noise, but now we see that we are having twice as long as our training input here. So this will be x and this will be xval for validation and y validation. So now we have to decide what kind of network to use. We will try to find one which is as simple as possible for this task. So we choose a structure which is in principle able to approximate the function piecewise. So we will use a number of nodes in this network, and each node is in effect responsible for a piece of the function. We can do this with, for example, a 3-layer fully connected network with an activation. And you can also take a look at this tutorial explaining a multi-layer neural network and also the neural network model. So this is some reference of what we are doing. In our example, the first layer is the input layer, which takes one input sample of X and then distributes this sample to capital N hidden nodes with weights, and each node then has a bias which basically activates for certain value range of capital X, and the activation function, for instance the sigmoid function, which is mainly active in the input range of -4 to 4, followed by weights to the output layer, which in our case is simply one node which sums up all the inputs from the hidden nodes with weights but no activation function. We can see the structure of this network in this picture here. So we have our input sample, we'll have our input layer that will take this input sample and then we'll distribute to n hidden nodes with weights, and each node will have a bias and activation function, and then they will be followed by the output layer that in our case just will add all the inputs from the hidden nodes with weights but without any activation function.